Hey guys, coffee. So because that LaCroix there, you can see it, is giving me so much heartache and pain, I decided to get a far superior oscilloscope, and we will talk about it in a bit more detail at the end of the video. But I needed an usable oscilloscope, so thanks Phil for sending this in for a repair. It's actually fully working right now, but it's got a problem. So initially, and the reason why I didn't actually make a video about it was this scope had no sweep. So the horizontal sweep generator wasn't working, and the trace was filling up about 2 divisions worth of space on the screen. And I downloaded the schematics, and I'll link them in below, off of Keysight's website, of course, because they still keep schematics and service manuals for every piece of test gear HP ever made. And that's why I think HP is the best company to have ever existed, and that's why I promise I will do that video entitled An Ode to HP at some point. And I looked through the thing a bit, and I poked around, and I noticed there's a few sections. So this is the repair. I'm going to tell you what I did to get to the repair. So there's a few things that the schematics show you, and basically they just split the oscilloscope in its functional blocks, basically. So you have the front end, the attenuator is the front end, the caps here are actually covering thermally matched JFETs. I don't know if you can see that. I will bring you in for a closer look if I remember. And the cap is meant to ensure thermal tracking between the JFETs. You have loads of compensation and adjustments, blah, blah, blah. This is the power supply section, which is completely ridiculous. So there's 2 screws coming in from the bottom, holding the heatsink, which pokes out the back here, stuck onto the voltage regulators that supply the plus minus 12 volts. There's a giant row of diodes right in there. By the way, I'm using a chopstick because this is an authentic Japanese ceremonial chopstick that my mom brought from Japan. Hi, Mom. This is the power supply section, and we have some capacitors. A couple of them are looking a bit puffy, so that might be the root cause of the second issue. And then we have horizontal amplifier, vertical amplifier for the deflection plates, and there's a sweep generator in this area. I don't know exactly where the delay line for the trigger is. I'm suspecting it's underneath here somewhere, because the other side of the instrument is occupied by the cathode ray tube, and the high voltage generator, the bias supply, is underneath there. So how does an analog oscilloscope work? Well, basically you have a oscilloscope tube, which has a filament in the back, a few control grids and stuff like that, and it has 2 pairs of capacitors basically inside, 2 pairs of deflection plates, and they're 90 degrees apart. And there's an anode which accelerates the cloud of electrons. It gets focused and corrected for astigmatism and sphericity and stuff like that, and then it passes in the middle of those deflection plates on its way to hit the phosphor screen, and there's 2 signals being applied. One of them is the horizontal, which is a sawtooth waveform, which goes like this and then quickly plummets back to negative. So it's a plus minus 100 and something volts centered around 0, applied symmetrically to both plates. So each plate is seeing the symmetric waveform to the other. And the input signal is basically fed into the front end, amplified, and then it's fed into a similar sort of differential amplifier, which drives the vertical deflection plates. and those are responsible for shifting the beam up and down. And the beam shifting up and down gives you basically the representation of the signal in time. One thing to note is when the sawtooth collapses and goes back, pointing the electron beam to the start of the screen, the blanking grid of the tube is activated, which cuts basically the electron beam. It blocks it so it doesn't hit the phosphor screen, because you would have artifacts of retracing. So beam flying back across the screen would actually leave a trace on the phosphor and lead to wrong signals. So front end power supply, voltage regulators, transformer, vertical and horizontal amplifier, trigger and delay, and everything else like sweep, time base basically. And we have the input switch. This is for the time base, and these identical modules are the input attenuators for the vertical basically. And we have offset position for vertical, and we have another control which is the horizontal position. This had almost no effect on the sweep, so that's how I figured out what was wrong with the thing. And let me quickly tell you how I fixed the first issue. So I think you can see there's a resistor here. Let me actually bring in for a closer look, and I'll tell you about what happened. Right, so you can see this resistor here actually is a 33.2K. It used to live right here. And there's a sister of it. Basically, it's a symmetric circuit. It's two identical circuits basically. This resistor looked a bit suspicious, a bit fishy. I don't know what was wrong with it. I didn't know what was wrong with it, and then I measured the voltage across this one. I don't remember exactly what I got. I measured across this one. I got the full 200 and something volt supply for the deflection circuit. So I knew immediately that there was something very wrong. And if we take a very close look at the resistor, we'll be able to tell that it had suffered some heat damage. It's a metal film resistor, and I think you can actually even see a popped hole in it, if this thing would focus. So this resistor is completely open. I took out the resistor after a lot of struggles trying to take this bar out and desolder it from the other side, clean out the holes with this thing, and I bodged together a 33K resistor because I didn't have anything similar, and then I corrected the trace so it fills an entire screen and it's relatively centered, and I made sure the time base was still accurate with a signal generator and everything. But as it turns out, the scope isn't still fully working and there is a modulation in the beam intensity. So when you have a beam that's sweeping a bit slower, so under, I don't know, slower than a millisecond per division, you can see some modulation in the beam intensity, which means, to me, there's something wrong with the power supply. Now, how do we know there's something wrong with the power supply? Well, the rest of the thing works fine, but there might be something wrong with with either of the power supplies. So first of all, with the low voltage power supply that we have here, or the B plus supply. Now, I don't think there's anything wrong with the B plus supply, and there's two reasons. The high voltage supply. The first reason is that all the functions of the oscilloscope were regarding that would be affected by a malfunction of the power supply for the high voltage are intact. The focus is intact, the astigmatism is intact, the beam is nice and sharp, everything works fine. However, that's not excluding a problem there. But the second reason, and the far more convincing one, is that if you trigger the oscilloscope on the line, so if you use line trigger and you set it to, I don't know, 10 milliseconds per division, you can kind of see that the modulation is at about 100 hertz, which means that it's derived from a poor linear power supply. So either a busted diode, a leaky capacitor, or something like that. And lo and behold, and I apologize for the movement you'll see, because I'm not, I don't have enough camera gear to do this smoothly, but yeah, it wasn't so bad, was it now? Right. This capacitor here gets pretty hot. Actually, all of them get quite warm, but this one gets too hot to touch, and this one is a bit swollen. Actually, I'm not sure if you'd be able to tell. So, next step right now is I don't have 22 microfarad 250 volt capacitors, but I do have a bag of these very nice KXG Nippon Chemicons that I got at the flea market for, so 50 pieces of this capacitor were 10 bucks or something like that, 10 euros, something like that. So I think that they'll be a suitable replacement. And there's another couple of values of capacitor that I am sure I have, because this is a 4.7 microfarad 200 volt, and I remember swapping out a few in my electrometer, and I'm certain I bought more than I need. So let me take this apart and show you how to take it apart. I'm going to try and take it apart as carefully as I can. I think it's kind of meant to be serviced, but we'll see. And then afterwards, I'm going to replace these capacitors, put it all back together, and show you the front. Right, so that was a bear. Jesus Christ. Okay. So we have, first of all, this is obviously the trigger, because now that I see that the lane line is in here, we can actually take this cap off and you'll be able to see the delay line. It's beautiful, coiled coax, and it's basically just a very, very long wire, long transmission line. And these two connectors, which I had no idea what they were doing, are actually the actual delay line connections. And if we look from the back, we actually see that they weren't voltage regulators, they're voltage regulating transistors. Apologies. The most pedantic amongst you will try to chastise me for this. And here's our suspected culprits. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 capacitors, which I shall try and replace. First of all, though, there's a large number of diodes here, which could also be part of the problem, and let's take a look at those first. But even before that, this is the power module, the power transformer. Can you see the switch here? This is the main input switch for the entire oscilloscope. It's controlled by, it's controlled by one of those cable things, which is, so a cable in a jacket. And if I press the power switch from the front, can you see it pop up like this thing here? It's resisting my force, see? Because I'm pushing it from the other side. This is the single most ridiculous switch solution I've ever seen. It's very clever, but it's very, very hard to get back into place because this thing slots into the power module like this, and you have to both nail the location correctly so as not to shift the what do you call them, the thermal pads, but also not get the switch locked into the thing, because otherwise it will assemble correctly, you'll put the thing back together, and you'll realize that pushing the power switch does absolutely nothing. Ask me how I know. 3 times over. Right, so as you can see, the PCB quality is just superb. It's gold plated. It's absolutely beautiful. Very high quality components for the time. I'm going to have to clean this off with isopropyl alcohol and apologize for that. I got thermal paste all over my fingers and yeah, contaminated this glorious board. And I'm gonna just set it aside. Don't worry, everything here is ESD safe. Safe as in I don't care if there's ESD, because, you know. Oh, and look what I was just telling you. Can you see the gunk next to that capacitor? That's a very good thing that this board is gold plated, because leaky capacitors usually don't corrode gold tracks. Alright, so let me take out a multimeter and let me just quickly run through those diodes, because I want to make sure that they're all okay. Can you see the meter screen? Yes, you can. Right, let's go. Now let's go the other way around. See if. Okay. 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 Those 2 volts I was seeing there are basically the capacitor recharging in the opposite way, in the opposite polarity. Okay, so I'm pretty sure that the diodes are going to be all right, and let me just figure out what capacitors I need to change. So these are all 470 microfarad, which is good. These are all 222 microfarad, which is good, and these are all 4.7 microfarad, 250 volts. Okay, let me find those capacitors and be right back. Right, so I'm not even sure anymore. These are all 470 microfarad, 25 volt, 1, 2, 3, 4. 470 microfarad, 63 volt, smaller even. These 2 are 22 microfarad, 250 volt. I have 450 volt ones. These 2 here are, sorry you couldn't see them. These 2 are 4.7 microfarad, 250 volts. I have 4.7 microfarad, 350 volts. And these small ones here are 100 mic, 16 volts. I have 220 mics, 63 volts. They should be fine, I hope. And I am now going to, yep, can you see? Can you see? All right, so I'm going to fire up the soldering iron, and I'm going to take all these out, but I need to mark the negative first. So yeah, that's gonna be quite nasty. I'm gonna take a marker and mark a blue dot for negative. So negative, negative, hope I can see that. Negative. You know what? I'm gonna do this one at a time and carefully, and I'll just let the camera running, and then I'm gonna do a time lapse basically. So I think you saw another time lapse when I took the thing apart. I'm gonna try and show you another one now. Right, so I put all the capacitors back in. I did put one in a bit crooked. I'm sorry. Deeply sorry. OCD is very important in electronics. Now I'm going to clean this board off camera, and I am going to reassemble the entire thing, if I still remember how, because yeah, that's gonna be interesting to say the least. Let's try and do it together, shall we? Assembly, I mean. So, first of all, you take this and you carefully slide it back in here, avoiding all the wires, and you position it so that the pokey bits poke through the required pokey things in the front. And then we take the delay lines, and apologies, I'm doing this at a quite an off angle, and kind of a hard hole to get. Oh Jesus, I'm making a fool of myself. Okay, he must have time. There we go. That should be easier. And of course, me actually forgot that order of operation is important, and put the one closest in first. So now, oh, look at that. It went in without a hitch. Right, next. This is gonna be fun because I did write down all the wires and where they're supposed to go. So next up, I think we're going to plug this thing back in and try and get the compensation trim wire thingy out through the requisite hole, which I forgot where it was. Probe adjust should be right below the potentiometer, so not there. Maybe here? Nope. No, they're right here. We got a very chaotic energy going on. So it should be. Whoops. Where did this thing come through? Forgot completely. No way. These. Oh, this is gonna be fun. I forgot about these things. Right, so. Of course. Of course. Yeah, this is not gonna be fun. I'll be right back. Right, that was a proper nightmare, I swear to God. Jesus. I still haven't figured out where this is supposed to go through. But I'm assuming that it's supposed to go through one of these holes in the front panel. Or the wire. And if I manage to put this thing back together, I shall be very, very happy. Oh, right. I think it went through below and through here. Maybe? No? I could watch my footage back and figure it out that way, but where would the fun be in that? At least this way you get to see me suffer for my crime of dismantling a beautiful HP, and it's definitely not there. Holy moly, I really don't remember where it came through. This thing is a bear to put back together. Finally. God damn it. Okay, now, next thing on the list is, first of all, I've gotten very good at plugging these things back in. And let me just quickly do that. Alright. Of course I jinxed myself. I understand why YouTubers complain about having a camera. Right, and now we need to plug the wires back in, and I wrote a little thing. Let's see if I still remember. So these should be the filament wires because they're the thickest, and they should go here and here. And now we have red and white here, and plain red here, and we have a blue should be here. Oops. A yellow wire. I don't know if you can see what I'm doing. I'm sorry. Yellow should be here. A yellow and white should be here. Black Oh, no, sorry. BL blue. Oops. Yep. It didn't even reach. And we have this big connector which should fit somewhere in the PCB like this. And we have a red going here. And there's one more wire which I know is coming from the transformer box. So it's back together. The wire coming from the transformer box connects here. Okay, so now that we have this secured in place, let's, I think that's all the wiring. Let's do a smoke test and connect everything back together, plug it in, and see if our modulation issue disappeared. And then I'll reassemble it. Cheers. Now, by the way, surprisingly, the set screws for all the potentiometers, the knobs on the front, are imperial, because of course they are. And I think the wrench that really worked on these, the Allen key, is actually, so this is a Fender bridge setter thing. So this sets the saddles on a guitar. And it's the perfect size actually for that. Okay, now, very important. If you work on one of these oscilloscopes, push the plunger in here as far as it will go, and then we need to, I'm gonna try and reframe here. Just give me a few seconds to reframe so you can see what I'm doing. Oops. Sorry. Excuse me. Okay, so this is quite a difficult balancing act. Sheesh. And this thing is quite heavy as well, so we need to re-secure that. Like so. This should go to the other side of this board. This and this are the grounds, and they need to stay here. And now that we have this thing here, it's just a matter of whack, pull up, and it's caught. And now, yes, finally, first try. Yeah, baby. Okay, let's plug this thing back in here. And let me just, whoop, around the back. And there should have been a threaded screw with a washer. I think it's this one. The whole oscilloscope has got like 3 or 4 screws, so it's not that complex of an assembly, but it's very mechanically, like, weirdly put together. I don't know if that makes sense. And of course it's not that one, because why would it be? I think it's this ridiculously long one in here. And yeah, that looks about right. I'm honestly a bit nervous, apologies for my hand blocking the review, honestly a bit nervous of whether actually it's gonna work or not anymore. I sincerely hope it does. And let me reframe a bit. And let's get the trusty power cable. And, whoops. You're drooping a bit. And stick it back in. And fingers crossed. very hard to get a grip on these screws without, you know, I forgot what the panel does. So we need, okay, and one of the channels, either one, and that's the trigger. And let me adjust the intensity. Position maybe? Oops. Yeah, the focus is way off, and the position of the sweep is way off. Focus. Right. And yay, it works. Apologies, but and the modulation is gone. Whoop-de-doo. Right, so I actually talked for about 15 minutes by myself without it actually recording. So today's not my day. I'm still not out of coffee yet. So what's the conclusion? Tell us. Well, it works. It didn't catch on fire. You're looking at a something megahertz. It's many, I think it's 10 megahertz right now. And let's turn it down a bit. It's modulating with a 10 kilohertz frequency. So yeah, it works. It's a great little oscilloscope. I'm really tired. This thing was very, very not pleasant to work on. I mean, don't get me wrong, it's a very nice scope. Oh yeah, sorry. So I'm over its bandwidth. Literally over its bandwidth. So now we can see the modulation. Okay. And if we screw around with a trigger, we should get it perfectly in there. So now it's about megahertz modulated with 10 kilohertz, and this is 100 hertz. This is now a hertz, and you can see that it's breaking up into basically one time it's drawing one line, next time it's drawing the modulated line with the different amplitude, etc., etc. So it works. It's flawless actually now. And yeah, this was kind of, as I said, not a great experience to work on. So let's just do this carefully, and we can call it a day. I think this video is going to be far too long, so I'm gonna probably do some sort of clickbaity title. And yeah, I don't know. I love analog scopes. They're very pretty. The signal generator that I have isn't very great anymore. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . It's still another HP. Let me know if you wanna see inside that before I take it back. Alright, sorry, I'm rambling. Closure, finishing the video. Let me just grab another sip of coffee. Cold coffee. Right, yeah, a few changed capacitors. I actually counted wrong, and I still have one spare of these 470 microfarad capacitors. They seem to not affect the functionality of the scope by any means, and signal looks just as nice and crisp as it did before. And yeah, I'm not sure if you're gonna be able to see that there's still a tiny bit of, I don't think you'll be able to see it. I can't, at least. So maybe you can see a tiny bit left of the thing. To my eye it looks great. To the camera it might look a bit I don't know, hard to tell. I'm looking at the camera right now, so no, screen looks fine. Not entirely sure, maybe a tiny bit. But if you crank up the brightness just a bit, so it's not even halfway there, I'm gonna call this a good one. And I'll see you next time. My phone's almost dead. I got 3 missed phone calls. I have a few mails, and I missed Rotary SMP's live stream. So, and I wasted, not wasted, weekend's almost gone. Yay! Tomorrow's Monday. Okay, catch you next week, guys. See ya.